Hello, I'm Hyun-Myung from the University of Michigan. Today, I'm going to talk about non-equilibrium Green-Kubo relations for hydrodynamic transport. This work has been done in collaboration with Ji Gao and Jordan Horowitz in the same group. Phenomenological hydrodynamic equation will describe macroscopic relaxation to a homogeneous state. For example, suppose a simple fluid has a spatial inhomogeneity. As time goes, the particles move from dense region to a sparse region. In other words, the particle flows against the density gradient. The speed of relaxation is determined by the transport coefficient d. For equilibrium systems, statistical mechanics provides microscopic grounds for hydrodynamic equations. The fluctuation dissipation theorem proves that the fluctuation described by correlation functions and the dissipative response to the perturbation are proportional to each other. Here, A is a thermodynamic variable and the perturbation changes Hamiltonian by a small amount. One consequence of a fluctuation dissipation theorem is a Green-Kubo relation. Green-Kubo relations equate the transport coefficient to equilibrium correlation functions, connecting macroscopic and microscopic theories. However, this connection doesn't remain valid far from equilibrium, because the fluctuation dissipation has been only proved for equilibrium, but the fluctuations and responses are still related to each other even far from equilibrium. As a simple example of a non-equilibrium system, I use a fluid of active Brownian particles. An active Brownian particle consumes energy and propels itself with a speed of v naught in the direction of theta. In this example, we assume a pair interaction between active particles, which is first force F. And the two kinds of noises change the position and propulsion direction of a particle randomly. This system doesn't have a perturbation to perturb. Instead, we perturb the system by applying a weak force. Then the response function is related to a steady-state correlation function again. But to determine the conjugate quantity Q, we often need to know the expression of a non-equilibrium steady-state distribution. Since the steady-state distribution is hard to find for non-equilibrium systems, this fluctuation response equality is hard to use. Now the question is there any perturbation that connects the fluctuation response equality to hydrodynamic theory in non-equilibrium? Our answer is yes, and the perturbation is as follows. We assume the microscopic dynamics is Markovian, whether deterministic or stochastic, when the probability distribution follows the master equation with a generator L. The generator L can be a Poisson bracket for Hamiltonian dynamics or a Poker-Flanck equation of the active Brownian dynamics or a matrix for a discrete system. We perturb the system by changing the generator with this particular form. The perturbation is turned on slowly from a steady state and suddenly off at certain time, which we call t equals 0. We prove that the response function due to this perturbation is equal to correlation function between A and X. The conjugate quantity X comes from the perturbation, and it can be anything we want. No information about steady-state distribution is required. Although this equality is true for specific initial ensemble due to the particular choice of the perturbation, it can be still useful for hydrodynamic slow variables because the macroscopic behavior exhibit only in a long time and large length scale after the initial transient behavior dies out. Now, let's go back to the active Brownian particle example. Regardless the system is in non-equilibrium, the phenomenological hydrodynamic equation should be true because the particles still flow against the density gradient. More generally, any local density of a conserved quantity is a slow hydrodynamic variable and follows a hydrodynamic equation in a large time and length scale. In the Fourier space, it is clear that the small k mode of such a variable changes slowly because ak dot is small. The theory I'm presenting here is valid for any hydrodynamic variable. So we can have a perturbation that connect dispersive response to correlation functions of hydrodynamic variables in non-equilibrium. The dispersive response is again related to the transport coefficient D, so we could derive a non-equilibrium Green-Kubo relation. I present the resulting relation without the derivation. The form of relation is basically same as equilibrium Green-Kubo relations, but the static structure factor loses its thermodynamic interpretation because there is no solid non-equilibrium macroscopic thermodynamics. On the right-hand side, there is a correction term to the current-current correlation. This term is usually missing in equilibrium because of the time reversal symmetry. We confirm the validity of non-equilibrium Green-Kubo relation with numerical simulation of active Brownian particles. The interaction is chosen as a repulsive short-range force. We measure the transport coefficient D by two independent methods. First, we observe the relaxation dynamics. From the speed of relaxation, we directly measure the D. Second, we deduce the transport coefficient using the Green-Kubo relation. To do this, we measure three correlation functions. To see the relaxation, we first put the particle in a narrow region at the center of the system. Then we let them free to diffuse. As the hydrodynamic equation predicts, the first Fourier modes with the smallest k decay exponentially, and the exponent depends on k values. By measuring the slope of 10 independent samples, we could estimate d and its error. We also measured three steady-state correlation functions to deduce d from the Green-Kubo relation. To this end, we observed the long trajectory of a particle density and current. Assuming the ergodicity of dynamics, we can measure the correlation functions. For example, current correlation functions measured in this way shows an exponential decay from which we get the time integral term of the Green-Kubo relation. The other two correlation functions were also measured from the trajectories. We performed the simulation with 5 different propulsion speed V0 and 2 different interaction strengths K. The transport coefficient measured by two methods coincide within the error bars. For the case of a small V0 and large K, an approximate theory does not coincide with the simulation, but the two symbols are still overlap there, which demonstrate the validity of a Green-Kubo relation. In this talk, I showed that there is a perturbation that provides a fluctuation response equality that is useful to derive non-equilibrium Green-Kubo relations. The Green-Kubo relations was confirmed by numerical simulations of active Brownian particles by measuring the transport coefficient in two independent ways. Our theory is valid for any closed system as long as microscopic dynamics Markovian and complements other approaches based on projection operator method or Onsager's regression hypothesis. The theory can also apply to other kinds of hydrodynamic variables due to a broken continuous symmetry. We numerically confirm the resulting Green-Kubo relation for those variables using the Kuramoto model, which can be found in our paper. If you are interested in the details of our work, please find our paper on arXiv Thanks for your attention.